21st of April, a SpaceX rocket carrying two highly accurate atomic clocks blasted off to the International Space Station. One of these clocks, called PHARAO, was designed right here at the Laboratoire Temps Espace of the Paris Observatory. This clock is so accurate that it will have an error of just 1 second in 300 million years. To find out more about this extraordinary timepiece and the mission it is part of, I am now joined by Philippe Laurent, who is the Science Project Manager of PHARAO. Thank you very much for your time.
Thank you.
What are these two clocks doing on the International Space Station?
You know, in physics, we have some issues. The first one is to try to unify the four fundamental forces. So we can unify three of them. It is a strong, weak, and electromagnetic. And with gravity, which is the fourth one, we have difficulties. The general relativity is not compatible with the quantum mechanics. So the question is, what is the validity limit of the general relativity? Another question is about how are stable these four fundamental forces. And we have also another problems with gravity. You know dark matter, dark energy, what is that? How it is coupled to the matter. And so we have to answer all of these questions. To try to answer these questions, physicists have developed a wonderful instrument. It is the atomic clocks. So atomic clocks are based on the measurement of internal atomic resonance, which depends on the three fundamental forces, weak, strong, and electromagnetic. And also by comparing two distant clocks, which is this comparison is sensitive to the gravity, we are able to also measure the general relativity context. So with the same hand, we are able to have the four fundamental forces inside one instrument. So it is the main objective of the ESIS mission managed by the European Space Agency, ESA. So we will have the best clock of the world, in different countries, Europe, Japan, and US. And we will also have the best clock in space, which is PHARAO. And by comparing all these clocks, we'll be able to set a limit of the general relativity by comparing all these clocks from space to ground to space. So we can improve the previous measurement on the general relativity by 1 order of magnitude or to find some anomalies. It is the goal.
Okay. Can you tell us about the specifications of PHARAO, how it was developed, and how long did it take for you to develop this clock?
Yes, a long time. So we started in 93, 94 with a collaboration with Laboratoire Temps Espace and CNES. In the same year, we are also developing a new concept of atomic clock, which is called the atomic fountains. And these clocks use the cooling process, the laser cooling process to cool the atoms. And these atomic clocks was the best clock in the world. It is this one, in 1994. And when we feel that a limitation of this kind of clock was the gravity, because we have cold atoms. With the gravity, these cold atoms fall down, so the observation time of this atom is not so long. Well, maybe we can have better if we go to space, because we have no gravity and we can observe atoms very long time. So it's why we have started this project of cold atomic clocks. So the first part, we have developed a prototype just to demonstrate the feasibility of a kind of clock. Well, you see it is a big apparatus, so we have to reduce the size to miniaturize the clock. Yeah. So we have developed this prototype. We have demonstrated its operation during a parabolic flight in the zero-G airplane of CNES in 97. And in 98, we have proposed a mission to ESA, the ESIS mission, and this mission was accepted by ESA. And after that, CNES was responsible of the development of the flight model of the PHARAO clock, and ESA, the development of the other instruments.
Can you tell us about the other clock of the ESIS mission and how will these two clocks function?
PHARAO is primary frequency standards. That means it defines the second with high accuracy. But this clock does not operate all the times. So we need another clock to keep all the tick of the times continuously. And it is the goal of the hydrogen maser, which is another clock. So PHARAO control the interval time of the hydrogen maser, and the hydrogen maser send its signal to microwave link to transfer time towards the Earth. And on the Earth, we have the same. We have also microwave link to send information towards the International Space Station.
Can you tell us about the Laboratoire Temps Espace?
So the Laboratoire Temps Espace is responsible for the development, the improvement of the reference in space and in time, by using astrometry, by calculating rotation of moon, of the Earth, and by using time and frequency metrology. And in time and frequency metrology, we distribute the French legal time, and we also participate to the calculation of the TAI, Temps Atomic International. So we distribute our reference, but we are also developing new reference, new atomic clocks. We improve, you search other atoms, and we develop a new generation of atomic clocks.
We are now on the rooftop of the Paris Observatory, where a ground station has been installed to communicate with PHARAO. What does this ground station consist of?
These ground stations are connected to the atomic clocks here, and this ground station communicates with atomic clock on board the ISS to transfer the time signals and to be able to compare time on board and time in space. Usually we use only one antenna, but to perform some calibration in time, we need a second antenna to perform this calibration. And this second antenna will travel in the different labs, which are also equipped with ground station, to calibrate our station.